Hey, you're hanging with hanging with Hussick. This video is about molecular polarity. How do you know if a molecule is polar or not? So, as I said, this is about molecular polarity. So, make sure you realize the realm in which we're working here. So, we're talking about molecules. And since we're talking about molecules, it's really important you have a robust understanding of this vocabulary term. When you see the word molecules, you should realize that this means these are small single units that have covalent bonding in them, okay? This is not about ionic bonding, okay? This has nothing to do with ionic compounds. This is not about metals that have metallic bonding. Okay, this is also not about giant covalent molecules like silicon dioxide, network solids like diamond or graphite. This is not about that, really. This is about covalently bonded little discrete units that we call molecules. And we're assessing whether or not they are polar. So, are they polar or are they non-polar? That's the question, okay? Another thing we could say is if they're a polar molecule, we say they have a dipole. They have, in particular, a molecular dipole. And we might also say that they have a dipole moment. These are all terms that we use. And what it really means is to be polar, to have a molecular dipole, or to have a dipole moment, is that one side of the molecule is positive and the other side, or the other end, however you want to think about it, is negative. Is there a charge separation across the molecule? That is going to be the question. Is a molecule polar? What to look for? So you need to look for two really important criteria. There's two criteria you need to evaluate about this. Number one, are there polar bonds? Okay, so remember we've got bond polarity and we've got molecular polarity. If the answer to this is yes, there are polar bonds, then maybe the molecule is polar. Okay, so a polar molecule has to have polar bonds. So maybe the molecule is polar if you look at its bonds and yes, it has polar bonds. If the answer to this question is no, then you just stop. It's non-polar. Okay, it has to have polar bonds if it's going to be a polar molecule. The second criteria you look at is the shape, or as we more correctly say, the geometry of the molecule. In other words, you need to know its Lewis structure. So this is why we try to really emphasize the importance of being able to accurately determine the Lewis structures for molecules, because you need to know the accurate Lewis structure in order to evaluate whether or not a molecule is polar. Okay, so you need to know its Lewis structure. If you get to this point and you say, yep, it's got polar bonds, and then you make the Lewis structure, you are evaluating in the Lewis structure, do the bond polarities cancel out? Okay, do the bond polarities cancel out? If they cancel out, okay, then it's non-polar. If they do not cancel out, in other words, like if we have one end of the molecule which is sucking electrons closer to it, leaving the other end partially positive, and they don't cancel out, then it's polar. So if the answer is no, then it's a polar molecule. Okay, so I'll show you this with exemplars. So maybe the easiest way is I'll show you a few molecules which are certainly polar, and then ones that are non-polar. And just one thing I want to get out of the way is that ions are always polar. Any ion you come up with, whether it's a polyatomic ion like nitrate or sulfate, or whether it's just like a halide ion, or whether it's a metal ion, whatever, they're all polar. Okay, so let's knock that feature off right away. Never mind the rules for them. If they have a charge, we just say they're polar, because they do everything that a polar molecule would generally do. Okay, Let's take one that's maybe a little less obvious, but probably the second most obvious thing that you've heard your whole life is polar in science class, which is water. We talk about the water molecule being really important to know about as a polar molecule. So let's go through the criteria for it. So firstly, does it have polar bonds? What's the bonds like in there? Well, the bonds are two of these OH bonds, and we know that OH bonds are polar. What makes those OH bonds polar? Well, in short, they're not the same atom, the O and the H, okay? And so since they're not the same atom, we know that they're going to have a difference in electronegativity, right? So the oxygen and the hydrogen, since those are different atoms and they have different electronegativities, there's going to be a difference in electronegativity in this bond. And what we would actually observe is that the electrons get pulled a little bit closer to oxygen than they do to hydrogen, and that's because oxygen is more electronegative than hydrogen. So you don't really have to calculate the delta En. You could, if you had a list of electronegativities, which hopefully you do. You could put them in and see what's the difference in electronegativity. You'd find out there's a significant difference. You would declare these bonds polar, okay? So let's say yes for sure. The bonds are polar. Second criteria we need to then evaluate is the shape, okay? And if you look at the shape and draw the proper Lewis structure for water, you should come up with the fact that oxygen has the two lone pairs down there, okay? And so the shape of this, we call it bent, okay? Or we maybe call it V-shaped, whatever. So since it's bent, and since it has polar bonds both pulling in this general direction, there would be a resultant polarity in the molecule. And the resultant polarity, just to keep it clean, I'll draw it again. The resulting polarity we would represent like this, okay? We would put an arrow that points to the negative end, and then the tail of the arrow would be the positive end. So since those two polar bonds are pulling towards oxygen, the oxygen end is going to be partially negative and the hydrogen end is going to be partially positive. And so this is how we would represent that this molecule is polar. Okay, it has a dipole moment, whatever you want to say. Okay, compare that to something that's distinctly non-polar. Any of these diatomic species like this are going to be non-polar. Okay, so for example, let's show O2, all right? O2 would have a double bond, lone pair, lone pair, lone pair, lone pair, octet rule satisfied. Is there a polar bond? Are the bonds polar? No, they're not. So forget about it. There's only one bond in there, an oxygen-oxygen double bond. Oxygen and oxygen are the same atom, so there's going to be no difference in electronegativity, so there's no polarity, so you can forget about it. Same with this. We only have, same with F2 and I2. The bonds don't have polarity, so they're non-polar. Well, what about something where the bonds do have polarity, like CO2? If we make the Lewis structure for CO2, we're going to come up with this. And indeed, these bonds are polar. The CO double bond is polar, and each of them pulls in opposite directions. Okay, so you'd have a partially negative, trying to draw the little sigma negative, partially negative O's and a partially positive carbon, okay, in the middle. Well, now we go to criteria 2. And criteria 2 for this is the shape. So if you know that the shape is linear, okay, for this particular molecule, and you know that the bond polarities are basically one pulling this way and one pulling that way, is there a resultant polarity? And if you've ever looked at vector analysis or vector addition, something you tend to do in higher level math courses, but I don't think it's that hard of a concept. It's like if you take something pulling 1 degree to the right and something pulling 1 degree to the left, what's the result? What's the ultimate result? Well, the result is no resultant vector. In other words, they cancel out, okay? So they cancel out and there's no polarity. This is non-polar. If you do vector analysis of vectors representing the polar bonds and the way they pull in 3 dimensions, and it turns out there's no resultant vector, you know it's non-polar. If you do the vector analysis and you end up with any resultant vector at all, you know that that means one side of the molecule is negative and the other side is positive, or at least slightly negative and positive, and you're going to declare that molecule to be polar, okay? So let's look at a couple more of these, and maybe that can help you. So CH4 methane, you can't read my writing, but that says, is it polar or no? Okay, is it polar or not? Well, first off, let's look at the bonds. Basically, you start with the Lewis structure every time, don't you? Make the Lewis structure. It looks like this. What do we have? We have the CH bond. Is that bond polar? Yes, of course it is. The electrons are actually going to pull a little bit closer to carbon than they are to hydrogen. It's going to make the carbon partially positive, and it's going to make each hydrogen partially... Oops, no, I said that backwards. It's going to make the carbon partially negative, and it's going to make each hydrogen partially positive. Okay? So, does this mean that the whole molecule is polar, or what? So then you look at the shape, and you know the shape is actually tetrahedral for this. Okay? And I'm in no way saying all tetrahedral molecules are this. They all are polar. All are non-polar. No, no, no. If you're thinking there's a hack like that, I would have given you that hack. Okay, you have to look at each molecule individually. So you look at this tetrahedral molecule, and you say, how are all the molecule polarities stacking up? Is there a resultant polarity? Well, one is pulling this way, and one is pulling that way, and one is pulling that way, and one is pulling that way. So that's a cancel, and that's a cancel, and actually they all cancel out, and this is a non-polar molecule, okay? If I had the three-dimensional ball and stick model in my hand, it's a little bit easier for you to see maybe that no matter how you approach this molecule from its surroundings in space, every single angle from which you would approach it, you'd feel the same partially positive pull because those hydrogens are on the outside, okay, equally distributed around the outside. So there's no charge separation across the molecule. Methane, CH4, is, in fact, a non-polar molecule. How about NH3? This is called ammonia. How about NH3? Well, once again, let's look at its bonds first. Are they polar? Yes, of course they are, because N and H are not the same atom, so they'll have a difference in electronegativity. The electrons will be pulled towards N and away from H. So it's going to result in these partial positives at H and partial negative at N. By the way, I keep saying partial, because technically you shouldn't say something's charged unless it's fully lost or gained an electron, but these are all kind of technicalities. Anyhow, we've got these polar bonds. What about the shape? What about the shape of the thing? Well, we know the shape is trigonal pyramidal, right? It's like a little triangle-based pyramid. So how are those vectors, if we think about those polarities as vectors, how are they all stacking up? Well, we have one that's pulling this way, and we have one that's pulling that way, and we have one that's pulling that way. If you did like head to tail on those things, okay, like you're supposed to do in vector analysis, you'd see you have a resultant vector like that, okay? So this is in fact polar. This is polar because at the top of the molecule, you've got a negative part, and at the bottom of the molecule down here, you have a positive part. So the dipole would end up looking like this, if you will. I can write it like that, positive end, negative end. So this is a polar molecule. So I could go on and on with examples, and there's probably more in your class notes, etc. But the question that you may be begging at the moment is, why does this even matter? Why do we care so much about what's polar and not polar? Well, it's because, among other things, that when we're talking about expecting interactions between molecules, we know that like dissolves like. In other words, we know that if we want to dissolve a polar substance, like an ion or a collection of ions, if we want to dissolve those into solution, we need a polar solvent. So you know that water does well at dissolving salt. Why? Because salts are made of ions, okay? And water is polar. Now, it may not be obvious to you, but there are many nonpolar solvents which are also really important. So a nonpolar solvent like hexane, okay, which is a hydrocarbon, 6-carbon hydrocarbon, maybe a little bit of foreshadowing into organic here, but hexane is nonpolar, okay? So since this is a nonpolar solvent, if we have some sort of nonpolar solutes, we would expect that this will be a better solvent for nonpolar solutes. Okay, so it's a good solvent for smaller hydrocarbons and for other nonpolar substrates. The other really critical factor, which is dependent on the polarity of a molecule, is what type of intermolecular forces will occur between molecules of that type. Okay, so in other words, like if you have a pure batch of ammonia, what kind of forces can we expect sticking into individual ammonia molecules to one another? And what we see is we have these three main categories of intermolecular forces. We have the van der Waals forces, London forces, or dispersion forces. All those names mean the same thing. And these are forces that occur in all molecules. Okay? We then have dipole-dipole force. These are forces that occur only between molecules that have a dipole. So they're only among polar molecules. Same goes for the hydrogen bonding type of intermolecular force, which is an extra strong version of dipole-dipole force occurring among tiny molecules which have N, O, or F bonded to a hydrogen. These only occur among polar molecules, and they're the strongest intermolecular force. So it's really important to first know if a molecule is polar to know whether or not it can have dipole-dipole forces and or hydrogen bonding. And so ammonia actually fits into both of these categories. It can do hydrogen bonding as a special dipole-dipole force. It also has dispersion force and London force, but the most significant type of intermolecular force it has is hydrogen bonding, and that's because we know it's polar and we know it satisfies this requirement. Okay, so there's lots more we're going to talk about with intermolecular forces in class and in subsequent notes. But first, understanding whether a molecule is polar or not is of paramount importance. I hope you found this video helpful.